Bismillah ar-Rahman ar-Rahim. I talk about the James-Stein estimator for the mean vector of a Gaussian vector of observations. Specifically, we have an unknown vector x, and this x is observed as vector y. Y is equal to x plus noise, a noise vector, eta. Eta is complex valued, circularly symmetric Gaussian with a zero mean vector and a covariance matrix, sigma squared times identity of size n by n. So the eta vector, the vector of noise or contamination, it has n components, eta 1, eta 2, all the way to eta n. It is a Gaussian vector. Specifically, it is complex valued Gaussian, and each one of those etas is circularly symmetric. So it is a circularly symmetric Gaussian vector. The components are independent, are zero mean, and the variance of each component. So if we take the expectation of the magnitude squared of eta j, that's equal to this sigma squared greater than 0, and sigma squared is assumed to be known. Eta is added to x to give us vector y. X is an unknown vector. Y, we can think of it as the observation vector, and it is a complex valued, circularly symmetric Gaussian vector with a mean vector x, and the covariance matrix is the same as the covariance matrix of eta. So also the covariance matrix of y is sigma squared times the identity matrix. Given y, so we have y. What is an estimate for x? So if we want the maximum likelihood estimate, okay, what is the BDF of y? The BDF of y is 1 over y to the power n, sigma to the power 2n, and then we have exponential minus the L2 norm squared between y and x, like this. Now, to obtain x via maximum likelihood estimation, we will try to find vector x that maximizes this likelihood function. And this, in our case, is equivalent to minimizing this L2 norm squared. And it is clear that the maximum likelihood estimate of x is y. So the estimation of x is vector y itself. This is an unbiased estimate. So the point of the James-Stein estimator is that we can construct an estimator that is biased. However, the mean squared error of that estimator is strictly, and we will prove this, smaller than the mean squared error of the maximum likelihood estimate. So our estimator now will not be vector y, but vector y multiplied by 1 minus b, which is a non-negative real number, divided by the L2 norm squared of vector y. So now this is vector y, like in maximum likelihood, but we subtract b, a non-negative real number, and we will assign a value to b near the end of this derivation, divided by the L2 norm squared of vector y times vector y. This is now our estimator. The task is to show that using such an estimator, the James-Stein estimator, will result in a mean squared error that is superior, so that is less than, strictly less than, the mean squared error in the case of the maximum likelihood estimator. Now for the maximum likelihood estimator, what is the error? So if we use maximum likelihood, the error, the estimation error is y minus x. So this will be the estimation error, and this will be vector eta itself. Now, what is the mean squared error? So the mean squared error is the expectation of the L2 norm squared of eta. So this is the expectation of eta Hermitian eta. And so this is the sum of the variances of the components of vector eta. So this is the dimensionality of vector eta, which is a small n, and we will take small n here to be greater than or equal to 2. Going back here, the expectation of eta Hermitian eta, which is the mean squared error for the maximum likelihood estimate, is n times sigma squared. Can we do better? And we will show that we can find a value for b, which is strictly positive, that will achieve a lower mean squared error. The estimation error is vector e, so that's an n-dimensional vector, and it is the estimator minus x, which is the vector to be estimated. So we have y times 1 minus x minus b over the L2 norm squared of y times 1. Y minus x, according to our model, that's the noise vector eta. And so the estimation error is eta minus b over the L2 norm squared of y times vector y. The mean squared error, by definition, is the expectation of E Hermitian E, which is the L2 norm squared of vector E. So we'll take the Hermitian of E times vector E, and so we will get 4 terms. So before applying the expectation, we will have eta Hermitian eta, this by this, and then here we will have B squared over the L2 norm of Y to the power 4, and then we will have Y Hermitian Y, and then we will have minus B divided by the L2 norm squared of Y, and we have Y Hermitian eta plus eta Hermitian Y. Now, eta Hermitian Y, this expectation is N, as we did here, is N sigma squared. And this term here is Y Hermitian Y divided by the L2 norm of vector Y to the power 4. But Y Hermitian Y is the L2 norm of vector Y squared. So this term here is B squared times the expectation of the reciprocal of the L2 norm squared of vector Y. And we start our investigation by focusing on this term, trying to get basically, or to evaluate this expectation. And then we will multiply it by B squared, and this will be a term in the mean squared error. Let's think about vector Y. Vector Y is again complex valued, circularly symmetric Gaussian with a mean vector of X and a covariance matrix sigma squared times identity of size n by n. Now, what will happen if we write down explicitly the L2 norm squared of vector Y? Y is a vector with n components, so we have y1, y2, all the way to yn. And each component has a real and imaginary part. So the L2 norm squared of vector Y is magnitude y1 squared plus magnitude y2 squared, all the way to magnitude yn squared. Now, each one of those guys is a complex quantity, and the magnitude squared is the real part squared plus the imaginary part squared. So the L2 norm squared of vector Y is the sum of 2n real valued Gaussian random variables. Now, if we divide vector Y by sigma squared over 2, then each of those guys is divided by sigma squared over 2, and each one of those guys now will have a variance of unity. Why is this the case? Note that vector Y is Gaussian and circularly symmetric. So it means that each component in Y has a variance sigma squared. Indeed, the real and imaginary parts of YK, so real YK and imaginary YK, are independent because the vector is circularly symmetric. So the real and imaginary parts are independent, and each of them has a variance that is equal to half the variance of YK. So if YK has a variance sigma squared, then this guy has a variance sigma squared over 2, and this has sigma squared over 2. So if we take those random variables and we divide by sigma squared over 2, so if we take this sigma squared over 2 into account, we have the following. We have the sum of 2n independent unit variance, sum of 2n, the real and imaginary parts, independent, because each component in Y is independent of each other component, and because Y is circularly symmetric, then the real and imaginary parts are independent of one another. So we have the sum of 2n independent unit variance real valued Gaussian random variables. But are those guys zero mean? No, they are not zero mean, because the mean vector of Y is vector X itself, which means that real Y1, it has a mean value of real X1, and the expectation of imaginary Y1 will be imaginary X1, and so on. So we have now this quantity here matches the definition of a non-central chi-squared random variable. It's non-central because our friends here are not zero mean, but otherwise they are independent and they are basically unit variance. They have a variance of unity each after doing this scaling. So we have a non-central chi-square. How many real valued Gaussian random variables do we have? We have 2n of them. So it is, this quantity is a non-central chi-squared random variable with 2n degrees of freedom. But then there is a non-centrality parameter, and the non-centrality parameter is basically the sum of the squares of the means. And so, as I said here, that the mean value of real yk will be the real part of xk, and the expected value of the imaginary part of yk is the imaginary part of xk. And so we will get this expression for the non-centrality parameter. And what we have here, before dividing by sigma squared over 2, this is the L2 norm squared of vector x. So the non-centrality parameter is lambda, and it is equal to double the L2 norm squared of vector x divided by sigma squared. Now, the L2 norm squared of vector y divided by sigma squared over 2, that's non-central chi-squared with 2n degrees of freedom. So we can actually write down its PDF. So what is the PDF of a non-central chi-squared random variable with 2n degrees of freedom and a non-centrality parameter lambda? So let's write this. So we have non-central chi-squared, and we have the non-centrality parameter is lambda, and the number of degrees of freedom is k. Then the PDF has this form: 1/2 e to the minus x plus lambda over 2, and then we have x over lambda to the power k over 4 minus 1/2, and then we have a modified Bessel function. Okay, so we have here I k over 2 minus 1. That's the modified Bessel function of the first kind. And then the argument of this modified Bessel function of the first kind is square root lambda x. Okay, so if we have our non-central chi-squared random variable with non-centrality parameter lambda and number of degrees of freedom is k, then this is the PDF. In our case, what we need to do is to use k equal to 2n. In the general PDF, just replace k by 2n. Okay, so this k over 4, it will become n over 2. This k over 2 will become n. We are interested in the expectation of the reciprocal of the L2 norm squared of vector y, because this is a term in the mean squared error if we use the James-Stein estimator. And so what we need is we need the expectation of this quantity. And so in terms of the non-central chi-squared random variable, basically this expectation here is the expectation of 2 divided by sigma squared z tilde. From this relation, we can take 2 over sigma squared outside, and so we need to evaluate the expectation of the reciprocal of a non-central chi-squared distribution with 2n degrees of freedom and non-centrality parameter lambda. And this will require that we take the PDF and we integrate the PDF after multiplying it by 1 over z. The modified Bessel function of the first kind, it has this expansion for nu that is a real number. We have that I nu of z is equal to z over 2 to the power nu, and then we have a summation k from 0 to infinity. Then we have z squared over 4. This is raised to the power k, and then we divide by the factorial of k and gamma of k plus 1 plus nu. Okay, so this is very important, and we will use it here. So we have here nu is equal to n minus 1, and the argument of the modified Bessel function of the first kind is square root lambda z. And so using this expansion, we will replace this I by the summation, and we will do the integration term by term. Note that everything here is real valued and non-negative. And so by tonality, we can do the operations in any order of our choice. Okay, so we will swap integration and summation. We will take the summation outside, and with it, we take the terms that depend on the summation index j, but do not depend on the dummy variable of integration, which is z. The terms that depend on z will be, after collecting the similar terms, we have z to the power n plus j minus 2. For example, this will come from, we have, just to keep track of what we are doing, we have z to the minus 1. This minus 1 comes because we are obtaining the first reciprocal moment of the non-central chi-squared random variable. So we have z to the minus 1. Then in the PDF of this random variable, we have n over 2 minus 1/2. Then when we expand the Bessel or the modified Bessel function, we will get from here square root z to the power n minus 1 over 2. That's n over 2 minus 1/2. Okay, and then here we have square root z raised to the power 2j, and so we get a j. So let's see. We have minus 1, and then we have plus n over 2 plus n over 2. That's plus n. We have minus 1/2 minus 1/2. That's minus 1, and then we have j. So collecting those basically guys together, we have z to the power n plus j minus 2. And then we have e to the minus z over 2. Again, this is a term in the PDF of the non-central chi-squared random variable. In this integration, we want it to look like a gamma function, and so we do change of variables, small gamma equal to z over 2. So we do the change, and then we end with an integration that looks like this: integration from 0 to infinity, gamma to the power n plus j minus 2 e to the minus gamma. So gamma, remember that gamma of x is integral from 0 to infinity, t to the x minus 1 e to the minus t dt. So this means that we have here this integration with respect to gamma gives with respect to small gamma, it will give us the gamma function, and the argument of the gamma function will be this power here plus 1. So we have gamma of n plus j minus 1. From the properties of the gamma function, we know that gamma of x is x minus 1, gamma x minus 1. And so this gamma of n plus j that is here in the denominator, it comes from, again, the expansion of the modified Bessel function of the first kind. Then we can write this gamma n plus j as n plus j minus 1, gamma n plus j minus 1. And by doing this, we can eliminate the gamma functions, and we end up with this term, which is n plus j minus 1. And our result for this expected value will be in terms of this series here. Let's see where we are now. We are investigating the mean squared error. The estimation error E is the estimator, which is vector y, the vector containing the observations. And now it has this term here, 1 minus the non-negative real number b divided by the L2 norm squared of vector y minus x. And recall that the vector of observations y is x plus the contamination noise eta. And this eta is complex valued, circularly symmetric with a zero mean vector and of covariance matrix sigma squared I n by n. So what we did is that we expressed the MSE using basically those terms. This one here is just n sigma squared. Now, on the previous page, we evaluated this expectation here in terms of this series. And now we shift our focus to this expectation here. Expectation of eta Hermitian y plus y Hermitian eta divided by the L2 norm squared of y. We also need to evaluate this expectation. Now, eta Hermitian y and y Hermitian eta, each one of them is a complex scalar, and these two quantities are the complex conjugate of one another. So I can replace these two guys by 2, and then I put the real part of eta Hermitian y. Now, eta itself is y minus x. So this is y Hermitian minus x Hermitian times y. And when we do the multiplication, we get y Hermitian y. And this is the L2 norm squared of vector y. So this is a real valued non-negative quantity, minus x Hermitian y. So the real part of this, if we take the real part of this quantity, we have y Hermitian y minus the real part of x Hermitian y. Now we take this and we divide by the L2 norm squared of vector y, which is exactly y Hermitian y. So we have 1. So when we do the division, we will have 1 minus the real part of x Hermitian y divided by the L2 norm squared of y. Then there is a 2, because again, we have a complex quantity plus its complex conjugate. So it's double the real part. And later we will account for this minus b that is here. Okay. So this expectation can be written as 2 minus 2 expectation real of x Hermitian y divided by the L2 norm squared of vector y. Define alpha as normalized vector x. So alpha is normalized vector x. Okay, so here I am assuming that vector x is a non-zero vector. Okay, so alpha is equal to x divided by the L2 norm of x, and because of this normalization, we have alpha Hermitian alpha is equal to unity. The L2 norm of alpha, or the L2 norm squared of alpha, is equal to 1. And alpha Hermitian x will be x Hermitian x over the L2 norm of x. So in the numerator, we have the L2 norm squared. In the denominator, we have the L2 norm. So alpha Hermitian x is the L2 norm of x. Now I will write y in this funny way. So y is equal to y. Y is equal to y plus alpha Hermitian y. So this is a term that should not be here. So we subtract minus alpha Hermitian y. So we can write y as this term, alpha Hermitian y, plus, and then we have these two guys. So we have identity minus alpha Hermitian all times y. Recall that vector alpha has a unity L2 norm. Alpha Hermitian is a matrix. This matrix is Hermitian and is idempotent. So its square is itself. This matrix is an orthogonal projection matrix. Specifically, it projects an n-dimensional vector in the complex space onto vector alpha, onto the span of vector alpha. And I minus alpha Hermitian, again, is a matrix that is Hermitian, that is idempotent. It is an orthogonal projector, or an orthogonal projection matrix that projects orthogonally onto the range of this matrix. And the range of this matrix is basically the orthogonal subspace, or the orthogonal subspace to vector alpha. Now our expression has the L2 norm squared of vector y. So we need to take the L2 norm squared of vector y. So vector y now is written as two components. And when we take the L2 norm squared, we will have the L2 norm squared of the first part, the L2 norm squared of the second part, and then we will have the inner product between these two guys. We will have the inner product and its complex conjugate. But actually, the inner product is equal to 0. Okay, we can know that it is equal to 0 from understanding how these projection matrices work, or we can just verify. If I take this vector Hermitian, it will be y Hermitian and then alpha alpha Hermitian, and then we multiply by this vector. So we have here, we are studying the inner product, and it is clear that if we multiply alpha alpha Hermitian by identity, we get alpha alpha Hermitian minus, then we have alpha Hermitian alpha, that's unity, that's one, and we end with alpha alpha Hermitian. So we have alpha alpha Hermitian minus alpha alpha Hermitian. The inner product of these two guys is equal to 0, which means that if we compute the L2 norm squared of vector y, we will have the L2 norm squared of this plus the L2 norm squared of that, and we do not need to bother about the cross terms. And so this is what we get. Note that in writing down this expression, I exploited the fact that those matrices are idempotent. Again, this can be verified by doing things the hard way. What is the L2 norm squared of this guy? So it is y Hermitian and then alpha alpha Hermitian, and then we multiply by the vector alpha alpha Hermitian y. Well, alpha Hermitian alpha is equal, and we end up with this term here, and the same for the other term. Note that identity minus alpha alpha Hermitian, this is a Hermitian matrix, so it has eigen decomposition. Matrix Q, it contains the orthonormal eigenvectors of matrix I minus alpha alpha Hermitian. Alpha alpha Hermitian has one eigenvalue that is equal to 1, and then n minus 1 0 eigenvalues. Matrix identity of size n by n minus alpha alpha Hermitian. Now this matrix, it has one eigenvalue that is equal to 0 and n minus 1 unity eigenvalues. So this means if we multiply Q by the matrix, diagonal matrix of eigenvalues, and then Q Hermitian, we get Q tilde Hermitian. Q tilde contains the orthonormal eigenvectors of I minus alpha alpha Hermitian corresponding to the unity eigenvalues. So I minus alpha alpha Hermitian can be written as Q tilde Hermitian, and note that Q tilde Hermitian times Q tilde will give us identity because the eigenvectors are orthonormal. So each one of them has a unity L2 norm, and they are orthogonal to each other. It is good to investigate Q tilde Hermitian times X or Q tilde Hermitian times alpha. From the meaning of Q tilde, and it comes from the eigen decomposition of this orthogonal projection matrix, those guys should be the O0 vector of size n minus 1, but we can do things in slow motion. Q tilde Hermitian times X, recall that alpha is equal to X over the L2 norm of X, so X is equal to alpha times the L2 norm of vector X. Now what we do is that we insert here Q tilde Hermitian Q tilde because this is identity. But then we look at these two guys. Q tilde Hermitian is the matrix which is identity minus alpha alpha Hermitian, and this is multiplied by vector alpha. Now this is I times alpha is alpha minus alpha and the scalar alpha Hermitian alpha, which is 1 because that's a normalized vector with a unity L2 norm. So we end up with alpha minus alpha, which is all 0. Keep this in mind that Q tilde Hermitian times X or Q tilde Hermitian times alpha gives us an all 0 vector. So the L2 norm squared of vector Y, so the first term is y Hermitian alpha alpha Hermitian y. This can be written as the magnitude squared of the scalar complex quantity alpha Hermitian y. And then the other term is y Hermitian, identity minus alpha alpha Hermitian y. Now from the eigen decomposition of this orthogonal projector, this is Q tilde Hermitian y. And so this can be written as the L2 norm squared of Q tilde Hermitian y. Okay, because if we expand this L2 norm squared, it will be basically this term, which is the quadratic form that we have in the expression of the L2 norm squared of vector y. Now, Q tilde Hermitian times y, y is x plus eta, and we agreed that Q tilde Hermitian x or Q tilde Hermitian alpha is equal to an all 0 vector. And so when we multiply Q tilde Hermitian by y, we get Q tilde Hermitian times eta, the noise vector. Gamma be equal to alpha Hermitian y. So this is alpha Hermitian eta plus alpha Hermitian x. And don't forget that alpha Hermitian x, because alpha is x over the L2 norm of x. So alpha Hermitian x is the L2 norm of x. And let W be this vector here, which is of size n minus 1 by 1. So it is Q tilde Hermitian times eta. So we have these two vectors. And if we collect them in a vector, let's say that this vector is big omega. So it's an n-dimensional vector. We have here at the top, we have the scalar random variable, which is gamma. And then here we have W. Now, this vector can be written in terms of vector eta, which is this noise vector, the vector containing the noise components that are added to vector x to yield the observation vector big Y. That's an n-dimensional vector. And now we can say that gamma is equal to alpha Hermitian eta. So this is a matrix that is n by n. Its top row is alpha Hermitian, and then the other n minus 1 rows will basically be q tilde Hermitian, which is a matrix of size n minus 1 by n. And note that gamma has this term, which is alpha Hermitian x, which is the L2 norm of x. So we need to have a factor here, which is the L2 norm of x, and then we have we put here n minus 1 zeros. So the idea is that vector omega, which contains gamma and w, so gamma and the components or the random variables residing in vector w, this vector is an affine transformation of vector eta. It's an affine transformation of vector eta, which is a Gaussian vector. So an affine transformation of a Gaussian vector yields a Gaussian vector. So this means that gamma and the components of vector w, w1, w2, all the way to wn minus 1, those guys are jointly Gaussian. And what is the importance of something like this? We will try to show that gamma and the w's, vector w, they are independent. But what we will do is actually that we show that they are uncorrelated. But since gamma and w1 and w2 and so on are jointly Gaussian, then uncorrelatedness implies independence. So proving independence just requires that we show they are uncorrelated. Okay, so this comes from the fact that gamma and w, they are related to eta via this affine transformation. Recall also that if our vector is complex valued and it is circularly symmetric, then the affine transformation of a circularly symmetric Gaussian vector also yields a circularly symmetric Gaussian vector. So now we have these two guys, gamma. Gamma has a mean of alpha Hermitian x, that's the mean value, and this is the L2 norm of x. And the covariance matrix of gamma will be, we take gamma minus its mean. So this will be alpha Hermitian y minus alpha Hermitian x. And then we take the outer product, this vector with itself. And so this will be the expectation of alpha Hermitian eta, eta Hermitian alpha. And then we apply the expectation to eta, eta Hermitian. Well, that's the covariance matrix of vector eta, which is sigma squared times identity. And so we end up with sigma squared, and then we have alpha Hermitian alpha is equal to 1. So this, the variance of gamma is sigma squared. So gamma is a complex valued circularly symmetric Gaussian with a mean that is equal to the L2 norm of vector x and a variance that is sigma squared. Now, w, the mean vector is equal to 0, and we can also, like what we did for gamma, we can compute the covariance matrix, and the covariance matrix will be sigma squared times identity. So w is a complex valued circularly symmetric Gaussian with a zero mean, and the covariance matrix is sigma squared times identity, and the size here is n minus 1. This is the important step. We will try to examine whether gamma and w are correlated. Okay, and so we will do the outer product. So we'll take vector w, and then we multiply by gamma Hermitian after subtracting the mean of gamma. For w, the mean vector is the all zero vector, so it is w minus its mean is just the w, and so we take the expectation of w times gamma minus expectation of gamma, all Hermitian. Well, this thing here is alpha Hermitian times u minus x, which is alpha Hermitian eta, and when we do the Hermitian here, we get eta Hermitian times alpha, and this is w q tilde Hermitian times eta. Now we apply the expectation. The expectation is basically applicable to eta Hermitian. That's the covariance matrix of eta, which is sigma squared times identity. And so we end up with q tilde Hermitian alpha. Recall that on the previous page, we showed that q tilde Hermitian times vector alpha or q tilde Hermitian times vector x gives the O0 vector. So when we study the cross covariance of w and gamma, we obtain an O0 vector. So this means that gamma, which here is this variable alpha Hermitian y, and the w, which is q tilde Hermitian eta, and basically these two guys are uncorrelated because the cross covariance is this all zero vector. But because they are jointly Gaussian, then they are independent. Okay, and they are jointly Gaussian because together they come from an affine transformation of vector eta. This is the quantity that we have in the expression of the mean squared error. It is the real part of x Hermitian y divided by the L2 norm squared of y. And so we can recall that alpha is equal to x over the L2 norm of x. So x is the L2 norm of x. We can take it outside, and then we can, rather than having x Hermitian y, we have alpha Hermitian y, which now is given the name big gamma. And then the L2 norm squared of y will be the magnitude of gamma squared plus the L2 norm squared of vector w, which we have here. W is w1 to wn minus 1. Each one of those guys, magnitude wj squared, which is the variance of wj. This is equal to sigma squared. So each component can be written as real part and imaginary part, and because the Gaussian vector is circularly symmetric, then for each component, the real and imaginary parts are independent, and each of them has a variance which is sigma squared divided by 2. Okay, so this means that if we take the real part of W1 squared plus the imaginary part of W1 squared plus the real part of W2 squared plus the imaginary part of W2 squared, and so on. So this summation here will give the L2 norm squared of vector W, and if we divide by sigma squared over 2, then we have sum of 2n-1. So we have n-1 random variables. Each one has a real part and imaginary part. So this is sum of 2n-1, 0 mean, unit variance, real valued Gaussian random variables. And so this distribution is a chi-square distribution with 2 times, between brackets, n-1 degrees of freedom. So the L2 norm squared of W, which we'll give here the name C, this is a random variable that is equal to the positive constant sigma squared over 2 multiplied by a chi-squared random variable with this number of degrees of freedom. And the chi-squared random variable has a standard BDF that we can use, and we basically adapt it to this specific number of degrees of freedom. The quantity of interest that appears in the mean squared error is the real part of alpha Hermitian y, that's gamma, so the real part of gamma, and in the denominator we have the magnitude of gamma squared plus the L2 norm of vector W squared. Suppose that gamma is equal to A plus, so we'll say gamma is equal to A plus IV, okay? And so those are the real and imaginary parts of gamma. So the fraction of interest here in the numerator, it has the real part of gamma, which is A, and in the denominator, there is the magnitude of gamma squared, so that's A squared plus V squared. And then we have the L2 norm squared of vector W, which we call C, and don't forget that C is sigma squared over 2 times the chi-squared random variable. Note that because gamma is circularly symmetric, then the real and imaginary parts are independent of one another. So the joint distribution of the real and imaginary parts of gamma, basically these two guys are independent. One of them, so this A, will be real valued Gaussian with a mean that is equal to the L2 norm of vector X and variance sigma squared over 2, while the imaginary part will be real valued Gaussian that is 0 mean, and the variance is also sigma squared over 2. Again, this is because the guys are, or vector gamma itself is circularly symmetric. And the reason it's circularly symmetric, again, is that gamma together with W, they come from an affine transformation of the circularly symmetric Gaussian vector eta. We now have expressions for the distributions. We know what is the distribution of C. We know the distribution of A and the distribution of V. Now we want to evaluate this expectation here. So this is the expectation of A divided by A squared plus V squared plus C. This A is the real part of gamma. A squared plus V squared is the magnitude of gamma squared, and C is the L2 norm squared of W. And so we will do it from the expression. We will have a triple integral in which we take this quantity here, which is A divided by A squared plus V squared plus C, and we multiply by the PDF. So it should be the joint BDF of A and V and C. But remember that gamma and the W are independent. We proved this by showing that they are uncorrelated, and hence they are independent because they are jointly Gaussian. And because A and V are the real and imaginary parts of the circularly symmetric gamma, they are independent. So basically, the joint distribution can be written as the BDF of A, the BDF of V, and the BDF of C. Okay, so this is the integral that we need now to evaluate so that we get this expectation here, which is needed for the mean squared error of the James-Stein estimator. The first order of business is that we will do a rectangular to polar transformation of A and V. So we replace A by U cosine theta and V by U sine theta. So in this case, dA dV, because we are now using polar, this dA dV becomes U du d theta. And U will be from 0 to infinity, and theta is from 0 to 2 pi. Now let's do first the integration with respect to theta. So what are the terms that depend on theta? So this A, when we do the change, it becomes U cosine theta. So we'll have a cosine theta here. And then we have also a cosine theta because this A here will be U cosine theta. So it turns out that the integration with respect to theta is a modified Bessel function of the first kind. Okay, so we can use this and write down the integral with respect to theta in terms of the modified Bessel function. Then to be able to proceed, we will repeat step that we did earlier, which is we will use the expansion of the modified Bessel function, as we will see on the next page. We are interested in this expectation. We started with a triple integral, and this triple integral involved the three independent random variables, a, v, those are the real and imaginary parts of gamma, and c, which is the L to norm squared of vector w. Then we change it from a to v to polar u and theta. We did the integration with respect to theta. This yielded the modified Bessel function I1. Now we write down this Bessel function using the series. And then we will do a particular change of variables here. We are left with a double integral with respect to u and c, u from 0 to infinity and c from 0 to infinity. So we will replace u divided by the square root of u squared plus c. This quantity we will call t. We are replacing c by t. Note that when c is equal to 0, then t is u over u, t is 1. And when c is equal to infinity, t will be equal to 0. So these will be the integration limits for the variable t. And again, after some algebra, dc will be equal to minus 2u squared over t cubed dt. And we will write down big S, which is this expectation here. Now, in terms of the variables, u and t rather than u and c, the integration with respect to u is still from 0 to infinity. The integration with respect to t is from 0 to 1. We write down our stuff. We collect the terms. For example, here we have u to the power something. We have here u to the power something. Here is a u squared that will go with this u squared and so on. So we make sure that we gather the similar terms and we end up with this double integral. Now, if we look at the integration with respect to u, it looks very much as something that can be written as the integral of the gamma function. And this is exactly what we will do. We will change u squared over sigma squared t squared here for a given t. We will call this thing h, so that we have here exponential minus h, and then outside we have h to some power, and we can express the integration with respect to u as a gamma function. So we get this integration with respect to h, and this integration will give us gamma of, and then we take this power of h and add 1, so we will get a gamma n plus j, which is this term here. Now we have one last integral, which is the integral from 0 to 1 of t to the power 2j plus 3 times 1 minus t squared to the power n minus 2. And this integral is a screaming beta function, because the beta function, if we have a beta function, it will be integral from 0 to 1, t to some power, 1 minus t to some power, and then dt. We have t squared here, so what we can do is do the change of variables, t equal to the square root of g. And now we can rewrite this integral as integral 0 to 1, g to the j plus 1, 1 minus g to the power n minus 2 dg. And this is exactly the beta function with two arguments. The first argument is this power here, plus 1, so this will be j plus 2. And the second argument will be this power plus 1, so this will be n minus 1. We know that beta of m and n, this is gamma m, gamma n over gamma of the sum. So we apply this rule here, and we end up with gamma of 2 plus j, gamma n minus 1, divided by gamma n plus j plus 1. And because from the previous integration, we have here gamma n plus j, and now we obtain gamma n plus j plus 1, then we can use the properties of the gamma function and write down this as n plus j times gamma n plus j, so that this gamma function will go away. So we do all these simplifications, and we end up with basically this expression here. It's in the form of a series. Now we collect our results and plug them in the expression of the mean squared error corresponding to the James-Stein estimator. And this is what we get. Okay, so these are the previous results. And the mean square error now will be n sigma squared. This is the expectation of eta Hermitian eta, or the L to norm squared of eta. And then minus 2b comes from here. And then there will be these two infinite sums. They are not the same. Okay, so here, for example, we have the term 1 over n plus j, and the other one is 1 over n plus j minus 1. But it looks that we can sort of combine them. But before doing this, we will assign a particular value to the parameter b. So remember, the estimator is 1 minus b over the L to norm squared of y, the vector of observations, all times the vector y. At the beginning, I said that b is a non-negative real number. Now let b be equal to sigma squared times n minus 1. So whenever you see a b here, replace it by n minus 1 times sigma squared. And doing this, this is our expression for this particular choice of b. Okay, so we just need to demonstrate that there is a choice for B that is strictly positive that will lead to a mean squared error strictly less than the mean squared error obtained when we use maximum likelihood estimation. Before trying to combine these two sums, in this sum, we replace j by j minus 1. So we get summation j minus 1 equals 0 to infinity, 1 over j minus 1 factorial, lambda over 2 to the power j minus 1, 1 over n plus j minus 1. So j will be from 1 to infinity. And then let's write 1 over j minus 1 factorial. Let's write it as j over the factorial of j. Then we have lambda over 2 to the power j minus 1. And then we have this factor here. Now it has the same form as the factor in the second sum. Note that after writing 1 over j minus 1 factorial as j over the factorial of j, we can rewrite the sum starting from j equals 0, because when j is equal to 0, this j in the numerator will make this term equal to 0. Note that in this summation, we have an outside lambda, which can be combined with this lambda to give lambda to the power j, like the lambda to the power j here. We will take n minus 1 sigma squared exponential minus lambda over 2 as a common factor. And then inside the summation, j from 0 to infinity, we have lambda over 2 to the power j. And then we have 1 over the factorial of j. It is here, and it is also there. And then we have 1 over n plus j minus 1. It is in both sums now. What is the difference? From this summation here, we have n minus 1 remaining after taking n minus 1 as a common factor. And from the first summation here, we will have 2 times j. Okay, so after taking the common factors, we will have, from the first summation, we have 2j. And from the second summation, we will have n minus 1, because there is n minus 1 squared, because there was a b squared. We set a value of b equal to n minus 1 times sigma squared. So this will lead to n minus 1 squared here. When we take n minus 1 as a common factor, we still have this n minus 1. Now, we take this quantity and we rewrite it in this form. I will rewrite this quantity as 2n plus 2j minus 2. There is an n. I made it 2n. We need to subtract n. 2j. We already have 2j. There is a minus 1 here. I made it minus 2. Then we need to add 1. Then this can be written as 2, open bracket, n plus j minus 1. And then we have minus n minus 1. Note that this n plus j minus 1 is like the term here in the denominator. We can take this and divide by n plus j minus 1 and separate the sum into 2 sums again. Now, after doing the separation, one summation can be evaluated, because if we take the outside factor, it is n minus 1 sigma squared exponential minus lambda over 2. And then we have summation j from 0 to infinity, lambda over 2 to the power j, 1 over the factorial of j. And then this will go with this, and we only have a factor of 2. Now, this summation is exactly e to the power lambda over 2. And it's multiplied by e to the minus lambda over 2. This product is unity. And we are left with 2n minus 2 sigma squared. We already have 2 minus n sigma squared. And if we add these two terms together, we get n sigma squared. But here is the very nice thing. When we split the sum into 2 sums again, now we have a minus sign. So after the splitting, this summation now can be evaluated. It can be written as an exponential, and then it can be combined with those terms here. But then we are left with another summation, and this summation is of positive terms when n is 2 or more, and it comes with a minus sign. So the mean squared error of the James-Stein estimator using b that is equal to n minus 1 sigma squared is strictly less than n sigma squared, which is the mean squared error if we use the maximum likelihood estimate.